Hi, I'm Melon Choi from Human Centered Systems Laboratory, Chungang University. Today I'm going to present MagSnoop, listening to sound induced by magnetic field fluctuation to infer mobile payment tokens. So Samsung Pay has emerged as one of the representative applications of the smartphone. Because Samsung Pay allows users to pay on an existing magnetic payment terminal, thanks to the magnetic secure transmission technology known as MST. Then, what exactly is MST? MST is Samsung's patent technology which enables wireless payment by mimicking magnetic card swipe. A magnetic stripe card is a plastic card with a band made of magnetic material. When you swipe them a magnetic card reader, the tiny magnets in the magnetic card induce current on the reader. This is the way that they communicate with each other. So similarly, MST can emulate the swipeable card using a built-in inductor coil called MST coil. When the MST is activated, it continuously generates an alternating magnetic flux called MST magnetic wave in the same form as the wave when you swipe a card on the reader. The weird thing is that the strange noises generated that you're listening to now, when the MST is activated, we call this MST sound. So this MST sound is already being noticed by several people online. Then, where does the MST sound really comes from? To understand the MST sound, we need to check out its origin. Most recent mobile phones include wireless charging modules. The modules contain ferromagnetic material to enhance the charging efficiency. The materials are composed of an internal structure called magnetic domains, each of which them has a magnetic direction. When the MST module is inactive, so no magnetic field is applied to the material is in a stable state because the direction of magnetic domains cancels each other. When the MST activates, applying the MST magnetic field to the material, the magnetic domains shift, extending the material itself. This phenomenon is called magnetostriction. More specifically, the intensity of applied magnetic field, H, and the magnetostrictive elongation, lambda, is proportional, which means the stronger the magnetic field, the longer the material becomes. In this way, the time-varying fluctuation of the magnetic field causes the vibration of the material, then propagate to the air, producing a sound. We observed that the MST sound is derived from the MST magnetic field. Therefore, they can contain sensitive information such as from MST magnetic field. So in this work, we deeply explore the MST sound and present MagSnoop, a severe security threat, listens to the MST sound to infer mobile payment token numbers. So, how the actual attack is performed using MagSnoop. Let's check out our attack scenario step by step. First, the attacker uploads his disguised malware to the app marketplace. The victim installs the malicious application on the smartphone. On the other side, in the store, the victim activates the MST to make a payment transaction. Meanwhile, in the phone, MagSnoop monitors the MST sound in the background using a built-in microphone. The MagSnoop application running in the background relays the MST sound to the attacker as soon as it detects the MST sound is playing. The attacker infers the MST token using MagSnoop, and the attacker replays the inferred payment token using MST device, making its own adversarial transaction. However, There are some challenges in realizing this attack scenario. Let's check it out one by one. The first one is the heterogeneity of target devices. As the majority of Samsung mobiles support MST, any one of them can be our target device. Since the structure of target device can be different, there will be a dynamic change in the shape of the MST sound. The second, and the second one is the presence of environmental noise. You know, the payment using Samsung Pay is done in a noisy place, such as a cafe or department store. These places usually have a high level of environmental noise, so this makes the MST sound even harder to detect. And third, the attacker should complete his malicious transaction before the victim completes his own payment. This is because Samsung Pay uses a one-time token, so it cannot be utilized once it's used. And the limited time also means a limited number of MST sound to analyze, because Samsung Pay MST signal every 1.5 seconds. According to our user study, an average user took 6.9 seconds after the activation to make a payment. In this case, we have only 4 MST sounds to analyze. This makes the problem even more difficult to solve, because MagSnoop needs to infer the payment token quickly with a limited number of MST sound to analyze. And lastly, the attacker needs to run the MagSnoop application sneakily. If the victim notices the app is doing something terrible, the attack might be impossible to complete. So we need to implement this application to be as quiet as possible. So how to enable this attack scenario addressing these challenges I've introduced? First, we need to deeply understand the characteristics of the MST sound, and then we fully utilize the characteristics we've explored to design MagSnoop. As I explained earlier, the fluctuation of MST magnetic field causes the vibration of the substances inside the phone and generate the MST sound. If you closely look at it, the direction of MST magnetic wave changes at the boundary of the bit. And each bit has one extra transition in the middle of the bit if the bit indicates 1. This encoding technique is literally called F2F encoding. We found that the sound produced this way have multiple frequency peaks having intervals of the clock frequency of the MST magnetic wave indicated as Fc when transmitting bit zeros. And transmitting bit ones will produce the MST sound having a doubled frequency as the frequency of MST magnetic field has doubled. So far, we have checked the fundamental characteristics of the MST sound. Our third observation was that magnets exaggerate the MST sound. Because the time is limited, I'll skip the details of this observation. Please refer to our paper for further information. Along with these characteristics we've observed, we first detect the MST sound among a noisy input sound segment and extract features that can be decoded easily regardless of the device model, and decode the actual payment token using 2 strategies. To detect MST sound among noisy input sound segment, we first utilize the dominant frequency of the MST sound we discovered. We first apply the bandpass filter to check out the dominant frequency where the MST sound is present. If the pattern of MST sound is detected, we catch it and continue to next step. After the MST sound is detected, we need to construct a feature that perfectly distinguishes between 0 and 1. Towards this, we construct a bandpass filter for a dominant frequency for transmitting a 1. Features extracted this way have more energy when its MST is transmitting a bit 1. and then smooth out the derived feature by taking the envelope of the signal. And there will be some feature set picked on multiple frequency ranges. In the feature, since a higher value indicates the bit 1, we need to pick the feature which clearly shows the peaks. We calculated a metric called maximum safe range as a height difference between the lowest positive peak and highest negative peak. In this way, a larger maximum safe range will mean more significant peaks. And then we adaptively select top 3 features that can distinguish 1 and 0 bits based on maximum safe range. If we extracted the feature correctly, all we need to do was to just make a right guess from the extracted features. But the problem is that we have only a few numbers of MST sound, so actually it is hard to make a right guess. So in this step, we make use of several decoding method and some uncertainty of the MST sound to build a rich token set that contains a bunch of regional tokens. At the end of the previous step, we have 30 candidate tokens extracted in different frequency with different methods. Thanks to the error detection technique that the MST token use, we can prune the illegal inferences to get the final regional token set. Throughout this process, the number of regional tokens is significantly reduced to about 7.12 tokens per a MST sound on average. After all, the application responsible for detecting the MST sound must act furtively. We use 2 methods to minimize the user's awareness of the application. The first one is to detect the MST sound only right after the screen is owned by a user. This assumes that the users tend to activate their MST transaction right after turning on the screen. This will significantly reduce battery usage. The second one is to set the notification icon as a transparent image. With this method, we managed to minimize the visibility of application to reduce user awareness. Noticeably, in our user study, none of the participants reported that they noticed an apps running in the background. Then, is MagSnoop able to accurately infer payment tokens addressing the challenges? And is MagSnoop able to conclude a tag in a real-world environment? We first conducted a micro-benchmark test on our system. The experiment is done in a flat surface. We check the inference accuracy of the MST sound. The metric inference accuracy is defined as a probability of having at least 1 right guess given n MST sounds. We used 3 victim devices. 2 foldable devices come with the built-in magnets to support the folding function, which Galaxy S10 5Z does not have. So we attached the commodity magnetic case to the phone to evaluate the effect of the magnet. Through our micro-benchmark test, we tested the inference accuracy of MagSnoop. As you can see on this side, MagSnoop can successfully infer the MST token with high accuracy given only 1 MST sound. This is thanks to the token set generation technique in the decoding step. Even with the limited number of MST sound, we can achieve a high inference accuracy. And with any device model except the S10 without the cover case, MagSnoop shows a significant level of accuracy. This is because we designed the system applicable to various device models in our device adaptive feature extraction part. On the other hand, without the magnetic case, S10 shows 0% accuracy. This is because magnetostriction is not strong enough to generate the MST sound without a magnet inside the phone. We also evaluated robustness of our solution against environmental factors. The noise robustness test is done in front of inbuilt speaker of a laptop. And we also evaluated the impact of usage case. Since we picked some robust frequency ranges against environmental noise, MagSnoop shows a pretty good result even with a 70 decibel of loud environmental noise. And we are able to see that there is no noticeable impact on the user activities such as holding the phone thanks to our robust design. After all, you might ask, does MagSnoop work in a real-world environment? To validate this, we conducted a real-world deployment test at a restaurant. In this case, the users had to order food using Samsung Pay. We had two different cases, each of which was to hand the phone over to the clerk to complete the payment, and the other was to take the phone to the terminal on their own. We consider an attack success if MagSnoop infers the token before the victim's payment. We can confirm in both scenarios, more than 60% of the case, MagSnoop was able to infer the payment token before the user completed the payment. When the user had to hand over their phone to the clerk, there is some time delay to hand over the phone to the clerk, so this means more time for MagSnoop to eavesdrop, so it shows a better performance. Throughout this presentation, we introduced MagSnoop, which leverages MST sound to infer the payment token number. Since this is a side channel attack that cannot be patched with a simple software modification, we strongly recommended that users pay attention to their phone's background recording status, and mobile vendors consider the risk of side channel attack on a magnetic communication device when used with permanent magnet. Thank you for listening to the presentation, and I'm happy to take any questions.